Hello, this is Professor Keene. Today what I'll be doing is lecturing on Newton's Universal Law of Gravitation. This is from Newton's Principia, Book 3. This is really the culmination of Newton's work. It's kind of the crown jewel of his Principia that's covered in this chapter. The reference is a student's guide, Volume 2, Chapter 27. And just by way of reminder, let me remind you that the background leading up to this point. First of all, Newton presented his definitions and his axioms. These are now known as his laws of motion. In these, he provided a relationship between the notion of force acting on a body and the change in motion of that body. So the force is a cause, and the change in motion is the effect of that cause. Then, in section 2 of the Principia, this was back in book 1 as well, what Newton did is he showed how the nature specifically of the centripetal force that is acting on a body can be deduced from the observed motion of that body. So for example, if you see a body that is orbiting around, sweeping out equal areas in equal times, you can deduce that there must be a centripetal force acting on it. And moreover, if there's certain relationships between the time of orbit and the radius, one can deduce the kind of centripetal force that's being applied. Then, in the phenomenon, which was at the beginning of Book 3, Newton described the observed motion of planets, such as Mercury, Venus, Mars, Jupiter, and Saturn, as well as their moons. This was really a review of the observations that had been made by many previous astronomers, including Johannes Kepler, upon whose work Newton largely bases his universal law of gravity. Now, what's going to happen is Newton is going to combine all of these lines of reasoning, his laws of motion, his propositions about centripetal force, and these phenomena or observations about the planets in order to construct a universal law of gravitation. He does this in 4 propositions or theorems. So what I'd like to do right now is talk about proposition 1 or theorem 1, which I have up on the screen right now. I'll read it and then I'll explain where he's going with this. So here it goes, proposition 1 or theorem 1. That the forces by which the circumjovial planets are continually drawn off rectilinear motions and retained in their proper orbits tend to Jupiter's center and are reciprocally as the squares of the distances of the places of those planets from that center. So this, again, sounds a little bit complicated, but it's actually pretty straightforward. So let's break this down and see if we can understand what he's saying. So if you're talking about these circumjovial planets, those, remember, that's an older term for the moons of Jupiter. And he's saying something about the forces that are acting on the circumjovial planets or the moons of Jupiter. He says the forces by which these planets are continually drawn off from rectilinear motions. That is, they would go in a straight line. That's the principle of inertia he's invoking. But because there's a force acting on them, they are removed from a circular line and they're retained in their orbits, right? And now what he's going to do is he's going to say something about those forces. First of all, he's going to make 2 claims. First of all, that, and maybe I'll underline this in blue, these forces tend to Jupiter's center. Okay, so that's the blue thing, the blue comment. And the second point that he's making here is, and I'll make this, I don't know, the brown point. These forces are reciprocally as the squares of the distances of the places of those planets from that center, right here. So I guess I could summarize this. The forces acting on the moons are pointed toward Jupiter. That's the first point he makes. And secondly, the forces, as he says, they are reciprocally as a square of the distances. In other words, the forces are proportional to 1 over the distance from the planet or the moon to the center of Jupiter squared. They're 1 over r squared or inverse square kinds of forces. So this is what he's proposing. And then in the paragraph after this, he is arguing for how he knows this. And I don't have that printed out here, but let me highlight what are the main points of his proof. So he's going to prove proofs of point 1 and 2. how does he prove these? Well, let's take them one at a time. He's really done all of the heavy lifting in developing the way of analyzing this. Now he's just going to cite some of his observations and propositions and so on. So how do we know that these forces are pointed toward Jupiter? Well, because of, he says, phenomenon 1, which he stated before. Remember, phenomenon 1 said that the moons of Jupiter are circulating around Jupiter. They're sweeping out equal areas in equal times. That was phenomenon 1. And then all he needed to do is invoke proposition 2 or theorem 2 of book 1, where he pointed out that if there is an object that its orbit is remaining in the same plane and it's sweeping out equal areas in equal times, that implies that there must be a centripetal force acting on it. So there you have it. He invokes the observations about those moons and this proposition, and he has demonstrated that there must be forces acting on the moons of Jupiter that are pointed inwardly toward Jupiter. Pretty straightforward proof. The second claim he's making in this proposition 1, theorem 1, is that these forces are specific kinds of forces. They're 1 over r squared or inverse squared forces. That means they get weaker and weaker the farther one is from Jupiter, and they're getting weaker and weaker in a particular way. That is, if you double the distance, the force is going to be 1/4 as big. If you triple the distance, the force will be 1/9 as big. So how does he know this? Well, he again invokes phenomenon 1, remember from the last chapter, chapter 26, where he noted that the moons of Jupiter, not only do they sweep out equal areas in equal times as they orbit Jupiter, but when you compare the orbital periods, the periods go as the orbital radii to the 3/2 power. That is, they obey Kepler's third law of planetary motion. And then all he needs to do is invoke proposition 4, corollary 6, which is what you tested in lab this week of book 1. And you might remember that in proposition 4, corollary 6, he points out that if objects rotating at different radii have periods related by, so I'll remind you, if the periods are related by the radii to the 3/2 power, then the forces acting on those that are holding them in orbit must go inversely as the square of the distances. This was an if-then statement that he demonstrated mathematically back in proposition 4, corollary 6 of book 1. So there we have it. Since those planets since those moons of Jupiter obey Kepler's third law, then there's an inverse square law acting on them, and that is the second point that he's making right here. Okay. There we have it, proposition 1, theorem 1. Let's go on to proposition 2, theorem 2. I will import this. Okay, let's move this down to, let's do this over here. And I'll probably do the next 2 propositions next time. Okay, so proposition 2, theorem 2. And again, this is in book 3 of Newton's Principia. Here, he claims, again, I'll read it first and then I'll break it down so you can understand it. He claims that the forces by which the primary planets are continually drawn off from rectilinear motions and retained in their proper orbits tend to the sun. And these forces are reciprocally as the squares of the distances of the places of those planets from the sun's center. Okay. So notice here he is talking about the primary planets. He's using the term primary planets because he was talking about over here the circumjovial planets. By that he meant the planets going around Jupiter, and by that we would call those the moons of Jupiter. So here he's talking about the primary planets. Those were the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. Remember, Uranus, Neptune, and Pluto were not known at the time of Isaac Newton. Now, he's considering the forces that are holding these planetary these primary planets in their orbits, right? These are the forces that keep them from going in a straight line, a rectilinear motion, and constraining them to move in an orbit, in a circle around the sun. He's saying two things. First of all, is that the force acting on them pulls toward the sun. There must be a force pulling them toward the sun. And secondly, I'm not doing my color coding thing over here. I'm not entirely happy with that. I'll just say it right here. These forces tend to the sun. And secondly, they are reciprocally as a square of the distance of the places of those planets from the sun. In other words, the force acting on the planets is proportional to 1 over r squared, where r is the distance of each planet from the sun. Again, it gets weaker and weaker, this gravitational force he's going to claim. Right now, we're just simply noticing that there is a force that gets weaker as you get farther from the sun. Okay, and so what he does in the paragraph following this proposition is he presents a proof of point 1 and point 2. So he's systematically going through this. How does he prove point 1? Well, point 1, now he simply invokes other phenomena. So first of all, he invokes in book 3, phenomenon 5. Remember phenomenon 5, that is where he was noting that the planets, when they are orbiting around the sun, they are sweeping out equal areas during equal periods of time. And if you consider equal areas being swept out in equal areas of time, and you also consider proposition 2 of book 1, going back to that, that's the same one we invoked over here. Proposition 2 of book 1 said that if, for example, you have something going in an orbit and it remains in a constant plane and also equal areas are swept out in equal times, that implies that there must be a centripetal force acting on that planet. So there we go. There's a force pulling toward the sun. He has proved it by phenomenon 5, the observation of the planets, and proposition 2 of book 1. The second point he can prove just as easily from phenomenon 4. Phenomenon 4, you'll remember, was claiming that when you look at the orbits of these planets around the sun and you compare any of their orbits, for example, the period of Mars's orbit compared to the period of Jupiter's orbit, and you compare the radii of their orbits, technically it's the semi-major axes of the orbits, but I'll write the radii, to the 3/2 power. So the periods of these two planets go as the radii to the 3/2 power. That's what he noticed. He pointed out in phenomenon 4. That is, these planets obey Kepler's third law of planetary motion. And then, once you recognize this, and then you simply invoke, once again, proposition 4, corollary 6 of book 1, where he says, if, same one over here, if two orbiting objects obey Kepler's third law of planetary motion, then the forces acting on them must vary inversely as the square of the distances. And that is precisely what he's claiming here. So notice what he's doing. He's building up a case that there must be forces pulling the planets toward the sun, and there must be forces pulling Jupiter's moons toward Jupiter, and moreover, the forces acting on the planets and the forces acting on Jupiter are getting weaker with distance in a particular mathematical form, that is, they are inverse square kinds of laws. Okay, I'm going to stop right there, having talked about propositions 2 and 1, and next time I'll talk about proposition 3 and proposition 4, where he's going to go on and talk about the motion of the moon around the Earth.